you'll see a lot is that we like to scale the equations out. So each term in that equation has a different kind of scale. And this is really important when it comes to fluid mechanics and fluid motion, because all of those terms aren't important at all scales, right? So sometimes the rotation is going to be really important, and sometimes the friction is going to be really important. And we represent that with these different scales. Okay? So when we're thinking about rotation, one important number is called the Rossby number. And that's basically the ratio of the effective terms to the Coriolis force. And the effective terms are from that time derivative that we're looking at, du dt, okay? When I write this out, it's actually the partial derivative with respect to time, so just how it's locally changing in time, and then plus this effective term. Okay, so I don't know if you guys taken vector calculus yet, but basically the fluid is changing locally with time, but it's also changing because the fluid is moving, and that's represented by advection. Okay, so if we're looking at the scales in this term, I guess let's take this product here. So the typical scale of the velocity we can represent by capital U, and then we have another capital U here because in that term, so we'll do a capital U squared. And then this is the gradient, so basically it's the derivative in space, so we can represent that by L. Okay, so that's where at that top we have U squared over L. Okay, and then if we recall the Coriolis force, just erase this here. The Coriolis force was F times K hat cross U. So again, K hat is just a unit vector, so it doesn't have a scale. So the scaling there would be F times U. Okay. So it's pretty simple. We get so the ratio boils down to U over FL.
What's L?
L is the typical length scale. So that came from that gradient vector when we're taking derivatives with respect to space. Okay. And so we think about this in terms of when would rotation be important. Well, that's when the Coriolis force would be a lot bigger than the effective terms, right? So looking at our ratio there, that would mean that we have a really small Rossby number, okay? Because the Coriolis force is really big. Okay, so next I thought we'd do a simple calculation. I think we can do it all together since there's not a lot of us here. So let's try to calculate the Rossby number for a draining toilet at our latitude. So I put up some helpful values here, calling what the Rossby number is. So for this problem, we're going to have to decide what our typical velocity scales and length scales are. Okay? So let's start off with the length scale for a toilet. That's pretty easy, right? So what do you guys think?
0.3 meters.
What?
0.3 meters.
0.3 meters, yeah, maybe on the orders of 10 centimeters. So let's take L to be 0.1 meters. Okay? Maybe that's a little bit shy, but that's okay. Now what about, well, F is pretty easy to calculate. Okay, so F was 2 omega times the times sine of theta. Okay, so we're at mid-latitude, right? So we're about 45 degrees latitude. So that would give us 2 times something to the minus 4 times 1 over root 2, right? So when we calculate that out, we're going to get something on the order of 10 to the minus 4, right? Because the 2 and root 2 there, that would just cancel out to be root 2, which is 1.4, so that's on the order of 1. So again, we're getting 10 minus 4. So now velocity scale. What do you guys think? What do you think the rate of rotation is for a toilet, or the rate that it drains at?
Like a couple times per second rotates around?
Yeah, like maybe in meters per second.
So 1 meter per second?
Yeah, that's a good guess, right? Maybe smaller. It doesn't take too long for the toilet to drain, right? So something small. So you would be maybe about we'll take Jay's guess, 1 meters per second. Okay. So what would we get for our Rossby number there?
10 to the 5.
Okay, so 10 to the 5. Okay. So what do you guys think? remember I said before that rotation was important when the Rossby number is really small. So Rossby number is on the order of 10 to the 5, then it's really not very important at all, right? So I guess the effect of if toilets do rotate different directions on northern and southern hemisphere, I'm not really sure. I've never been to the southern hemisphere. It wouldn't be because of the Coriolis force. It would be because of how the toilet is shaped, how the jets are springing. So those types of things give it some kind of preferential direction to flow. Okay. Did I have next?
So Simpsons was wrong.
Yeah, the Simpsons is wrong. So, okay, so demonstration again. If you guys don't believe me based on the math, let's go back to that ball demonstration. So I'm going to toss this apple to Jay. I'll let you know what I'm going to do.
Okay.
But first off, I want you guys to decide, do you guys think I'm going to have to take the effect of rotation of the Earth when I toss this to Jay? Right, no, that's ridiculous. So the scales are too small, so let's try it. No, I didn't, right, it got to him just fine. So if this doesn't matter, if this, like couples of meters here, if the rotation of the Earth doesn't matter there, then why would it even matter for the toilet, right? Okay, so that's all I have to say. Do you guys have any questions?
That's all I have to say for this part? Or
Yeah, I have, yeah.
Can you talk a little bit about what you do with that equation specifically in your research?
Okay, good. So maybe we can look at the equation again.
What kind of scale do you deal with?
Right. So part of my research is I'm looking at dust pickup on Mars and how that affects kind of bigger flows. So dust is known to affect the radiative transfer in the atmosphere, and that can have an effect on the temperature and the winds. So when I talk about this equation, this is the exact equation for fluid motion, but in reality, people don't actually use this equation, right? They make approximations. It's really, really hard to solve, even with a computer, solve this equation. This equation can represent gravity waves, like waves that are caused by differences in density. It can represent sound waves, so waves that are like the really fast acoustic waves, and all sorts of different scales. So the first thing I would do with this equation is to make some kind of simplification, and then I can look at a specific problem without worrying about all the other waves that are involved, and then I can use that simpler equation to solve my problem. So that's a bit of an explanation. And the Rossby number is pretty important for some of the stuff that I'm looking at. Any other questions? No? Okay, well, I have some for you. So Will asked me to make some problems. So these aren't too hard, but maybe I'll let you guys think about it for a bit, and then we can talk about them all together.